Welcome to the Drift into Quiet Knowing channel. Today we will travel back to the very first second after the Big Bang, not to witness a gigantic explosion in space, but to understand something deeper. Space itself was expanding, the temperature was dropping, and an extremely hot, extremely dense universe was beginning to shift from a state of intense energy into the first seeds of matter. This was a time with no night sky, no gentle starlight, no rock, no water, and yet the most fundamental processes were already unfolding. The forces of nature began to separate into their own roles. Elementary particles appeared, matter and antimatter almost completely destroyed each other. Quarks gradually combined to form protons and neutrons, and neutrinos began to separate from the boiling hot flow of matter in the young universe. The strange thing is that when we say 1 second, we usually think of something as brief as the blink of an eye. But in the early universe, that single second contained more change than millions of years that came after it. Each tiny fraction of the first second was like a different doorway. Behind it, the temperature changed, the density changed, and the way matter existed also changed. If those conditions had shifted even slightly, the later universe might have had no stars, no planets, no chemistry, and no us, sitting quietly and thinking about our own origins. So, on today's journey, stay with this slow and steady rhythm. We will not be searching for a mystical story. Instead, we will follow what modern science can say with caution and awe. Step by step, we will look into the first second of everything, when the universe had not yet created the world as we see it today, but had already laid down the first rules that would allow that world to appear. First, we need to step very slowly into an idea that seems simple, but is actually very easy to misunderstand. When people hear the words Big Bang, many often imagine a giant ball of fire exploding in the middle of darkness. In that picture, it feels as though a vast empty space already existed, and then the universe suddenly burst into it. But according to the way modern science describes it, that image is not correct. The Big Bang was not an explosion that happened in space. It was the expansion of space itself. There was no dark room outside for the universe to explode into. There was no fiery edge flying outward into the distance. There was no clear center where everything began shooting out like fragments. What was happening was that all the space we can trace backward with physics was in a hotter, denser, younger state, and then it expanded and gradually cooled. This is the first step in understanding the first second of the universe. We should not imagine ourselves standing outside, watching a glowing sphere grow larger. In the standard models of cosmology, there is no such outside position. If we could shrink the entire history of the universe into one very slow story, then in that first moment the most important thing was not where matter was flying. It was that the distances between points in space were changing. Space was not like a fixed stage already sitting there. It was part of the story. It could stretch. And as it stretched, the early hot and dense universe began to cool. Imagine that you have a very smooth sheet of fabric, and every point on it is much closer together than it is today. When the fabric is stretched, the points on it move farther apart, but no single point has to be the center of that stretching. This image is not perfect, because real space is not a sheet of fabric sitting inside some larger space. But it helps us avoid an important mistake. The universe was not matter exploding into a pre-existing emptiness. The distances within the universe itself were changing. And during the first second, that change happened so quickly that almost all of our familiar intuition stops being useful. When we say hot in everyday life, we think of fire, lava, the core of a star, or the surface of the sun. But the early universe was hot in a much deeper sense. It was so hot that the most familiar structures of matter could not exist. There were no molecules, no atoms, no dust grains, no rocks, no cold hydrogen gas drifting through darkness. Even the ingredients that would later form atoms were not yet in the stable forms we know. Everything was swept up in a sea of energy and particles colliding without pause. If any structure tried to form too early, that extremely hot environment would break it apart almost immediately. So, to understand a universe that was 1 second old, we have to set aside our image of the solid world around us. We have to enter a state where matter had not yet had time to become matter in the way we usually mean. This is very important because the question, how did the universe change during its first second, cannot be answered by saying that this star appeared, that galaxy formed, or some planet began to spin. All of those things were still far in the future. During the first second, the universe was changing at a much more fundamental level. Its temperature changed, its density changed, the way the natural forces appeared changed. What could survive longer than an incredibly brief moment changed? The universe changed from a state too hot for stable matter into a state that began to allow the first seeds of matter to have a chance to appear. There is a kind of humility that science has to keep here. The closer we move toward the initial moment, the harder the questions become. At extremely early times, so tiny that they are currently beyond direct verification, our physics is not complete. We have general relativity to describe gravity and the structure of space-time on large scales. We have quantum mechanics and particle physics to describe the very small world. But when the universe was extremely small, extremely hot, extremely dense, and strongly affected by gravity, those two regions of understanding need to be connected by a deeper theory that modern science is still searching for. So, when we speak about the deepest beginning of the first second, we should not speak with absolute certainty. We should speak like someone looking at traces, models, equations, and evidence, carefully separating what is well supported from what is still being studied, even so that caution does not make the story any less magnificent. In fact, it makes the story more beautiful, because we can see that science is not just free imagination. Science is the art of knowing what we can say, what we should not say too strongly, and what we need in order to open the door of understanding again in the future. We do not have a camera that was placed at the first second, but we do have traces of an expanding universe. We have the cosmic microwave background from a much later period. We have the composition of light elements. We have particle physics. We have models showing that a hot, dense, expanding universe could move from an early state into the vast universe we see today. From those traces, we can rebuild a story not through myth, but through tested reasoning. One of the most important ideas when we talk about the extremely early universe is cosmic inflation. According to many modern models, during a tiny fraction of the first second, the universe may have gone through a phase of extremely rapid expansion. The phrase, extremely rapid, is still too mild here. We are not talking about an explosion as fast as a rocket. We are also not talking about matter flying through space faster than light in the ordinary sense. We are talking about space itself expanding at a staggering rate during an incredibly short amount of time. This idea helps explain why the universe today, when viewed on very large scales, appears surprisingly uniform, even though extremely distant regions could not have exchanged signals with each other in any simple way during the later history of the universe. But we also need to be clear here. Cosmic inflation is a powerful framework with many reasons for indirect observational support, but its deepest details are still a subject of research. We cannot tell it like a fully recorded film. We can only say that if that phase of extremely rapid expansion did happen, then it did something strange. It magnified tiny fluctuations in the early universe, turning them into the seeds of later differences in density. Much later, under the influence of gravity, the slightly denser regions would pull in more matter and become the places where galaxies, galaxy clusters, and the cosmic web would form. So even though the first second had no stars, it may already have planted the first differences that would later give stars and galaxies a place to be born. Let us pause for a moment here. A universe with not a single star yet, but already carrying within it the conditions that would allow stars to appear. A universe with not a single planet yet, but already beginning to establish the temperature, a density, and expansion that would later allow matter to gather together. A universe with no atoms yet, but already on the path that would allow elementary particles, protons, neutrons, and eventually atomic nuclei to exist. That is exactly why the first second matters so much. It did not finish building the house. It laid the physical foundation so that the house would not collapse before the first idea of it could even take shape. After that extremely early stage, the universe entered a state that can be imagined as a hot sea of energy. But we need to be careful with the word sea. This was not an ocean of water, and it was not a cloud of fire in the ordinary sense. It was an environment filled with particles, antiparticles, and radiation, where every component was constantly interacting, being created, being destroyed, transferring energy, and transforming again. Light at that time was not gentle light travelling through a dark room. Photons, meaning particles of light, were trapped inside an extremely dense environment, constantly colliding with charged particles. There was no free beam of light travelling straight across the universe the way starlight reaches our eyes today. The universe was too dense for light to freely tell its story. For a more familiar image, imagine a room filled with steam so thick that you cannot see the wall in front of you. There is still light in the room, but it scatters everywhere and does not travel in a clear line to your eyes. The early universe was far more extreme than that. It was not only opaque in a visual sense, it was a hot plasma, where radiation and matter were locked together in a continuous dance of collisions. Later, long after the first second, when the universe cooled enough for electrons to combine with nuclei and form neutral atoms, light would be able to move more freely. But during the first second, there were no neutral atoms, no transparent space, and no sky to look at. There was only a universe boiling at the most fundamental level. That boiling should not be understood as water boiling in a pot. Boiling water is still water, made of water molecules that already have a fairly stable structure. But in the early universe, many structures could not yet be stable. High temperature meant that the average energy of particles was very large. Each collision could be powerful enough to create a particle and antiparticle pair, or to break apart connections that had just formed. As the universe expanded, the energy carried by each particle gradually decreased, like an intense piece of music slowly lowering its volume little by little. And it was that lowering that allowed order to appear, not order in the sense of quietness, but order in the sense that the laws of physics began to sort out what was allowed to exist. Here, we can feel a beautiful paradox. The universe has to cool down in order to become richer. When it was too hot, everything was blended into an extreme state, where familiar forms of matter had no chance to stand firm. As it cooled, the universe did not become poorer. It became more capable of distinction. This particle was different from that particle. This force had a different role from that force. More stable forms of existence began to separate from the shared background of energy. It is a little like a mass of molten metal cooling and crystallizing into a shape. The universe was like that too, but at a much deeper level. It cooled so that the laws and elementary particles could appear more clearly. We can imagine a sculptor who does not use a hammer or a chisel, but instead uses the falling temperature of all space. Each time the universe cooled, a new possibility opened. At extremely high temperatures, particles could not yet remain stable. When the temperature became lower, some particles could live longer. When the environment became less dense, some interactions were no longer fast enough to keep everything in balance the way they had before. Little by little, the universe moved away from a state where everything seemed to be swept into one shared storm, and toward a state where separate components began to have histories of their own. What is astonishing is that all of these first steps happened before there was anything the human eye could call scenery. There was no horizon, no surface, no colour in the familiar sense, nowhere to place a camera. If we say the universe was bright, that was not light shining inside a dark space. It was a state filled with radiation, but the universe itself was too dense for light to travel freely like starlight. If we say the universe was hot, that was not heat coming from an object in a room. It was the temperature of the cosmic environment itself, of every region of space in its younger and denser state. If we say the universe was dense, that was not a dense object sitting in a void. It was the energy and matter density of the universe itself, when distances were far smaller than they are today. So the first second was not a beautiful scene, in the way a painting can be beautiful. It was the largest natural laboratory that has ever existed, but no one was standing outside to observe it. In that laboratory, the expansion of space was the clock. The falling temperature was the rhythm of the scene changes. The falling density was the shifting stage. Elementary particles were the first characters, and the laws of physics were the quiet background music deciding who could appear, who disappeared, who could combine, and who could not remain stable. One point that is very easy to overlook is that the universe during the first second was not emptier than we imagine. It was actually fuller than anything we have ever known. The cold emptiness between the stars is the image of a much later universe, after billions of years of expansion. The early universe, by contrast, was a dense state of radiation and particles. The emptiness between galaxies today cannot be used as a model for the first second. Back then, there were no galaxies, so there could be no emptiness between galaxies. There were no stars, so there could be no darkness between stars. There were no atoms, so there could be no thin gas. In other words, the empty space, we imagine, is the product of a universe that has aged for a very long time. It is not the image of a newborn universe. This brings us back to the main message of today's journey. The first second did not immediately create the familiar world. It did not place the sun at the centre of a planetary system. It did not build the Milky Way across the sky. It did not create water in oceans or carbon in living bodies. Those things required enormous amounts of time. They required stars to be born and die, galaxies to gather, and heavy elements to be forged inside stars. But the first second did something even more fundamental. It established the conditions that allowed all of those processes to not be forbidden from the very beginning. It allowed the universe to move from a state too hot for stable structure into a history where structure could gradually appear. If we listen to this story very slowly, we can see that the birth of the universe was not like one loud moment that happened and then ended. It was more like a chain of deep phase transitions. In physics, a phase transition is when a system changes its state. Water becomes ice, vapor becomes liquid water, molten metal becomes solid. In the early universe, those phase transitions happened at the level of fields, particles, and forces. As the temperature dropped, the way the world worked changed. Things that had not been able to separate began to separate. Things that had been too unstable began to gain durability. Things that had previously been only possibilities in the sea of energy began to become real components of cosmic history. And this is why we need to begin the main body of the story with heat, density, and expansion, instead of rushing to talk about stars or galaxies. Because if we do not understand the original stage, it is very easy to turn the first second into the wrong story. We might imagine that the universe was just a giant firework, but the universe was not a firework. Fireworks explode in a sky that already exists. The early universe was the sky itself, the distances themselves, the temperature itself, the density itself, the very conditions that would later allow every sky to exist. In that first second, the universe did not need to be beautiful in the way human eyes want to see beauty. It needed the right conditions for matter to not disappear. If you keep only one image in your mind for this section, let it be this. Not a ball of fire exploding in empty space, but all of young space expanding, while a hot sea of energy gradually cooled. In that sea, there were no atoms, no stars, and no planets. But because of that expansion and cooling, the universe began to open the door to the next steps. The natural forces took on clearer roles, elementary particles existed within the hot environment, matter and antimatter entered a delicate balance, and quarks had the chance to combine into protons and neutrons. That is the quiet beauty of the first second. It was not like a scene to admire, it was like a rulebook being written through temperature, density, and expansion. And from that rulebook, billions of years later, the universe could finally have starlight, slowly turning galaxies, cold rocky planets orbiting distant suns, and a quiet mind asking, how did everything begin to change when the universe was only 1 second old? Once we have placed the early universe in the right frame, not as a ball of fire exploding in empty space, but as space itself expanding and gradually cooling, we can step deeper into a more subtle layer of change. The universe did not only grow larger over time, it also began to become more distinguishable. The things we now call natural forces, elementary particles, mass, electric charge, and interactions did not appear like separate objects being placed on a table one by one. They gradually revealed themselves inside an extremely hot environment, where the temperature of the universe decided what still remained blended into a shared state, and what had begun to take on its own role. In the world today, we're used to nature having several different kinds of forces. Gravity keeps us on the ground, keeps the moon orbiting Earth, and causes galaxies to gather together across the vast universe. The electromagnetic force keeps electrons bound to atomic nuclei, creating chemistry, light, electricity, magnetic fields, and every solid feeling of matter in everyday life. The strong nuclear force holds quarks inside protons and neutrons, and it also helps keep atomic nuclei from easily falling apart under the electric repulsion between protons. The weak nuclear force takes part in processes that transform particles, including radioactive decay and important reactions inside stars. In our cooler and more mature universe, these four forces seem like four very different ways for nature to act. But in the extremely early universe, when the temperature was so high that all everyday intuition becomes far too small, the way the forces appeared was not like the world today. At very high energies, some forces that now seem different can be described as different sides of a more unified structure. The clearest example in modern physics is electromagnetism and the weak nuclear force. Under present conditions, light, electricity, and magnetic fields belong to the electromagnetic force, while processes such as beta decay belong to the weak force. But at the extremely high temperatures of the early universe, those two forces are understood within a unified framework called the electroweak interaction. As the universe expanded and cooled, electroweak symmetry was broken, and the world began to distinguish more clearly between electromagnetism and the weak force. When we hear the phrase symmetry breaking, it may sound very unfamiliar, but the idea underneath it can be felt through a gentler image. Think of water. Water vapor, liquid water, and ice are all related to the same substance, but they behave very differently as the temperature changes. As vapor, the molecules move more freely. As liquid, they stay closer together and can flow. As ice, they settle into a more orderly structure. Nature has not replaced one substance with another. The temperature conditions make the same underlying physics appear as different states. The early universe was similar, but on a much deeper level. As the temperature dropped, fundamental fields and forces could shift from a more symmetric state into a state where their roles became more clearly separated. That matters because the first second was not just a simple cooling process. It was a series of changes in state. Each time the universe passed through an energy threshold, the effective rules of the world could become different. A certain type of particle could begin to have mass in a way it had not shown before. An interaction could become shorter range or longer range. Some particles could no longer be created as easily as before because the average energy of the environment had decreased. The so-called rules of the game were not written in ink on paper. They were written through the temperature, density, symmetry, and expansion of the universe itself. One of the important roles in this story belongs to the Higgs field. In the universe today, many elementary particles have mass because of the way they interact with the Higgs field. We should not picture the Higgs field as a sticky liquid that particles have to swim through. That is a common image, but it can easily be misleading. It is better to say that the Higgs field is a quantum field present in space, and the interaction of certain particles with that field is connected to their rest mass. When the universe was still too hot, the state of the Higgs field and electroweak symmetry were different from what they became later. As the temperature dropped past a certain threshold, the mechanism of electroweak symmetry breaking caused the weak force carriers, such as the W particle and the Z particle, to become very heavy, while the photon still had no rest mass. From that point on, the electromagnetic force and the weak force no longer appeared as a single face. This may sound very technical, but it touches the question we are asking directly. How did the universe change during its first second? It changed by causing the forces to no longer remain blended into a picture that was too symmetric to be familiar. It made the world begin to assign different roles. The photon became the carrier of the electromagnetic force, able to travel far and later form the foundation of the light we see. The W and Z particles carried the weak force, but because they were very heavy, the weak force acted effectively only across extremely short distances. That difference would become very important later. Without the difference between electromagnetism and the weak force, chemistry, light, nuclear reactions, and the history of stars would not unfold in the way that created the familiar universe. Let us pause here for a moment, because there is something worth thinking about. When you look at a candle, the light from that candle reaches your eyes through the electromagnetic interaction. When a star shines for billions of years, nuclear processes inside it involve the strong force, the weak force, and electromagnetism. When the atoms in your body hold their shape, the electromagnetic force is working quietly. But those roles cannot be understood properly unless we go back to the time when the universe was still too hot, when the forces had not yet appeared in the cool and familiar forms we know today. The peace of a star-filled night, in a very deep sense, was prepared by violent but silent transitions during the first second. Alongside the forces, there were also elementary particles. But here too, we need to be careful with the image of a particle. In everyday life, when we hear the word particle, we may think of a grain of sand, a speck of dust, or a tiny marble, something with a clear shape sitting in one place. In particle physics, the word particle is much more subtle. An elementary particle is not a tiny hard marble with a solid surface. It is an excitation of its corresponding quantum field, carrying energy, momentum, electric charge, or other properties, and it can interact with other particles according to probabilistic laws. In the early universe, those particles were not standing still like tiny objects in a room. They were constantly being created, destroyed, colliding, transforming and exchanging energy inside an environment so hot that everyday life gives us no real way to imagine it. Electrons and positrons are a beautiful example. The electron is the particle that later becomes familiar inside atoms, while the positron is the antiparticle of the electron. In the early universe, when the energy was high enough, pairs of electrons and positrons could appear from energy, and when they met, they could destroy each other and return to radiation. This does not mean they were created from nothing in some mystical sense. It reflects a deep principle of modern physics. Energy and matter can change form under the right conditions, as long as the conservation laws are respected. The young universe was a place where transformations like that happened constantly, because it was so hot and dense that each collision could carry enormous energy. Quarks and gluons open another layer of the story. Quarks are the basic ingredients that would later make up protons and neutrons. Gluons are the particles that carry the strong interaction between quarks. But when the universe was still very hot, quarks and gluons were not necessarily confined tightly inside protons and neutrons the way they are in the cooler world. They could exist in an extremely hot state called quark-Gluon plasma. We will look more closely at this part when we reach the moment when quarks combined into protons and neutrons. But even here, we can already see something important. The early universe was not a place where atoms were simply waiting to form stars. It was a place where ingredients deeper than atoms were learning how to exist in a world that was cooling down. Neutrinos were also part of this story, and they are almost like very quiet characters. Neutrinos interact extremely weakly with matter compared with electrons or photons. In the universe today, trillions of neutrinos can pass through our bodies every second and leave almost no trace at all. But in the early universe, when density and temperature were still very high, neutrinos still interacted often enough to be part of the shared plasma. Only when the universe continued to expand and cool did they gradually separate from that hot environment and follow their own history. That will become important as we move closer to the 1 second mark. But even now, the presence of neutrinos reminds us that the first second did not contain just one kind of matter. It was a chorus of many fields and many particles, each with its own way of interacting, each waiting for the right conditions to reveal its role. We can imagine the early universe as an orchestra in which every instrument is playing at an overwhelming volume. At first, our ears cannot tell what is the violin, what is the cello, what is the horn, and what is the drum. But as the volume lowers, each tone begins to emerge. This is not just a decorative example. It helps us understand one central point directly. As the universe cooled during the first second, it did not merely become less hot. It began to allow distinct physical roles to appear. The forces gained their own identities. The particles gained their own properties. The interactions that would shape the future began to leave their marks. And we should remember that this division of roles did not happen in stillness. It happened amid countless collisions. A photon could collide with a charged particle. A particle and antiparticle pair could be born and then destroy each other. Quarks and gluons exchanged energy inside the strong environment. Electrons, positrons, neutrinos, and photons all took part in a complex thermodynamic state. But within that complexity, physical order began to form. Order here does not mean silence, it means the stability of law. As conditions changed, nature did not become randomly chaotic. It followed probabilities, conservation laws, symmetries, and interactions. The young universe could be violent, but it was not meaningless. This also helps us avoid another mistake. We should not imagine particles being assembled like a worker putting parts together in a factory. The universe did not have an outside hand picking up quarks and placing them into protons, placing electrons into atoms, and then placing atoms into stars. Those steps happened because physical conditions changed. When the universe was too hot, some structures were not stable. When it became cooler, those structures became possible. When the density dropped, some reactions no longer happened quickly enough to reverse earlier results. When the rate of expansion competed with the rate of interaction, the universe began to freeze in certain important ratios. That is how the history of matter was written, not through mechanical arrangement, but through the balance between expansion, temperature, energy, and probability. If we look backward from the present, each of these things can seem like a strange chain of preparation. To have atoms, there first had to be nuclei and electrons. To have nuclei, there had to be protons and neutrons. To have protons and neutrons, quarks had to be confined inside more stable structures. For those processes to have time and the right conditions to happen, the universe had to expand at a suitable rate and cool in a suitable way. For photons to later travel freely and become light carrying information across space, the universe had to go through a long history, changing from an opaque plasma into something transparent. But all of those distant events began with a very fundamental reality in the first second. Forces and particles were no longer a blurry conceptual mass. They began to have their own roles in a cooling universe. This is exactly why the story of the natural forces is not a dry lecture. It is the backbone of the cosmic story. If the electromagnetic force did not appear the way it does, atoms would not have the familiar structure we know. If the strong force did not hold quarks and nuclei together, ordinary matter could not remain stable. If the weak force did not allow certain particle transformations to happen, the history of nuclear reactions in stars and the particle ratios in the early universe would be very different. If gravity did not pull slightly denser regions together over the millions and billions of years that followed, the first tiny fluctuations would not grow into galaxies. Each force has its own voice in the long music of the universe. But to hear that music, the universe first had to pass through those earliest moments, when the voices began to separate from the original noise of energy. We could also say that during the first second, the universe shifted from a state that was hard to distinguish into a state with clearer physical memory. Once forces and particles had their own roles, what happened afterward was no longer completely erased by extreme temperature. Some processes began to leave long-lasting consequences, some particle ratios began to matter, some imbalances, even very tiny ones, could become the foundation of the entire material universe. At this point, the universe still had no scenery at all, but it had begun to have history in a deeper sense. What happened in this moment would affect what could happen in the next. Let us ask a very quiet question. If we took away the division of roles among the forces during the first second, what would be left? The universe might still expand, but it would not necessarily have chemistry as we know it. The universe might still contain energy, but it would not necessarily have stable atoms. The universe might still have radiation, but it would not necessarily have long-burning stars, stable nuclei, or complex structures. That is why the separation of the forces into their own roles is not a small detail on the side. It is one of the conditions that allowed the later world not only to exist, but also to become diverse. We can feel this through a more familiar image. Imagine a completely dark kitchen in front of you, but all the ingredients, all the tools, all the flames, and all the recipes have not yet separated. There is no flour by itself, no water by itself, no fire by itself, no knife by itself, no table by itself. Everything is blended into a state that cannot be used. As the kitchen slowly lights up, each thing appears in its proper role. Fire is not water, a knife is not flour, a table is not a pot. Only when each thing has its own nature and place can a meal be cooked. The early universe was like that. It did not cook stars and planets in the first second, but it began to do something even more necessary. It distinguished the ingredients and rules so that, later on, every structure could be cooked by time. This story becomes even deeper when we remember that elementary particles are not only ingredients, they are also the way the universe preserves the possibility of interaction. The electron is not just a small particle that later sits around an atomic nucleus. It is the foundation of electricity, chemistry, atomic bonds, electric current in wires, and signals in nerve cells. The photon is not just a particle of light, it is the messenger of the electromagnetic force, the thing that would later carry light from stars to eyes and carry information from distant galaxies to telescopes. Quarks are not just a concept in particle accelerators, they are the components of protons and neutrons, meaning the deep inner components of the nuclei of every atom in rock, water, and the body. Neutrinos are not just hard to detect particles, they are traces of nuclear processes and of the early universe, an almost invisible stream of particles passing through history. But during the first second, all of those roles were only in their beginning form. There were no electrons inside atoms yet, because there were no atoms. There were no photons from stars, because there were no stars. There were no quarks resting quietly inside cold matter, because the universe was still too hot, and particle states were still changing. There were no fully free neutrinos in the later sense, because the early environment was still dense. The difference between there was no familiar world yet and the fundamental conditions were already there is what makes the first second beautiful. It was like a very early draft of the universe, without complete sentences yet, but with the alphabet and grammar beginning to appear. And now we can look back at the path we have just followed with one slow sentence. In the beginning, the universe did not give us a scene. It gave us a state. That state was too hot for atoms to exist, too dense for light to fly freely, and too young for stars or galaxies. But as space expanded and the temperature fell, the natural forces began to take on their own faces, elementary particles began to take on their own roles, and the first interactions began to draw the path matter would follow. The universe did not become familiar right away. It only became capable of becoming familiar in the future. This is where we see that the first second was not only the beginning of time in the storytelling sense, it was the beginning of distinguishability. Before that, everything was too hot, too dense, and too fast for familiar structures to stand still. After the first transitions, the universe was still violent, still filled with radiation, still without atoms, but it had gained a deeper order. The electromagnetic force would open the way for light and chemistry. The weak force would quietly participate in particle transformations. The strong force would prepare to hold quarks inside protons and neutrons. Gravity, though weak on the scale of particles, would later gather tiny seeds of density into enormous structures. And elementary particles, instead of being only foam on a sea of energy, would gradually become the first letters in the long story of matter. That was the moment when the universe began to have roles. Not acting roles on a finished stage, but physical roles inside a history that was opening up. There was no starlight yet, but there were photons. There were no atoms yet, but there were electrons and the particles that would enter nuclei. There was no rock, water, or biology, but there were forces deciding whether rock, water, and biology could exist in a far future. When the universe had passed through only tiny fractions of its first second, it was no longer a completely undifferentiated state. It was becoming a universe with laws, particles, interactions, and a path for matter to survive. And once the forces and particles had begun to appear more clearly, the next question became unavoidable. In that hot sea, particles and antiparticles were constantly appearing and then destroying each other. So why, after all those almost perfectly balanced annihilations, was any matter left at all? Why did the universe not become only a sea of light with no atoms, no stars, and no observers? That is one of the deepest mysteries of the first second, and it is also the next step in our journey. The moment when matter, through an incredibly tiny leftover amount, survived and became everything. And it is right here, after the natural forces and elementary particles began to appear more clearly in a cooling universe, that we meet an almost unavoidable question. Why is there still matter? At first, that question may sound far too simple, because we live in a world filled with matter. We sit on a chair made of atoms. We breathe air made of molecules. We see light from stars, from lamps, from the distant sky. Everything around us seems to confirm that matter is obvious. But when we go back to the first second after the Big Bang, the existence of matter is no longer obvious. It becomes one of the deepest mysteries of the entire universe. In the extremely hot environment of the early universe, energy did not simply sit still like an invisible reserve. Energy could turn into particles and antiparticles, as long as the physical conditions allowed it. A matter particle could appear together with its corresponding antiparticle. The electron has an antiparticle called the positron. The proton has an antiparticle called the antiproton. The neutron has an antiparticle called the antineutron. Quarks also have antiquarks. In many ways, antimatter is not strange in a mystical sense. It is not evil matter. It is not dark energy. It is not darkness with a will of its own. Antimatter is a symmetric counterpart of ordinary matter, with some properties that are the same, while some properties, such as electric charge, have the opposite sign. The strange part is this. When matter and antimatter meet, they can destroy each other and turn into energy. The word destroy also needs to be understood carefully here. They do not vanish into nothingness. They do not enter some metaphysical emptiness. Mass and energy are transformed according to conservation laws. After annihilation, the energy usually appears as radiation and other particles depending on the original particles and the specific conditions. In the early universe, when everything was still hot and dense, particle and antiparticle pairs could be created, meet each other, annihilate, and then their energy would take part in other processes again. The universe was like an ocean of particles, where appearing and disappearing were not meaningless chaos, but part of high-temperature physics. If matter and antimatter had been created in exactly equal amounts, and if there had been no mechanism to create a tiny excess of matter, then our story might have ended in a much colder way. Particle meets antiparticle. One pair destroys another. Matter and antimatter almost erase each other from history. As the universe expanded and cooled, what remained would mostly have been radiation, a sea of light and energy, but with almost not enough ordinary matter to make stars, galaxies, planets, rocks, water, or living bodies. A universe like that could still physically exist, but it would not have the familiar structures we're trying to understand today. And yet, our universe is not like that. We know this not because someone stood at the first second and counted every particle. We know it because when we look around, matter won, even though it won by an extremely tiny excess. Galaxies are made of matter, stars are made of matter, planets, gas, dust, ice, rock, oceans and biology are all made of matter. If antimatter still existed in large amounts across equally large regions, the boundaries between matter and antimatter would create powerful signs of annihilation, and we do not see that in the observable universe in that way. So the overwhelming existence of matter today tells us that there was an asymmetry in the early universe. Matter and antimatter were almost balanced, but not perfectly balanced. This is one of the most beautiful and most humbling moments in modern science. We know that there must have been some tiny imbalance. We know that the universe today is evidence of that imbalance, but we do not yet fully know how nature created the original excess of matter. Particle physics has observed some subtle differences between matter and antimatter, connected to what is called charge and parity symmetry violation. These differences show that nature does not treat matter and antimatter as perfect copies in every situation. However, the amount of asymmetry known in the current model does not seem to be enough to explain the full dominance of matter in the universe. So the question of why there is more matter than antimatter remains one of the biggest open doors in physics. Let us move slowly here. What remained to create everything may have been only an incredibly tiny excess. Many common descriptions say that for about every 1 billion matter and antimatter particle pairs that annihilated, perhaps only a tiny amount of matter was left, without a corresponding antimatter partner to annihilate with. The exact number depends on the description and the stage we're talking about. But the central idea is clear. The matter that makes up the universe today was not a large original portion that survived intact. It was more like what remained after an almost complete erasure, and that remainder, so small that in everyday imagination it would seem almost insignificant, became all galaxies, all stars, all planets, and all the atoms in our bodies. Imagine a very large room where almost every person wearing a bright shirt has a matching person wearing a dark shirt. Pair by pair, they meet and leave the room. The room slowly becomes emptier. Millions of pairs disappear. Billions of pairs disappear. In the end, only a very small number of people wearing bright shirts remain. So few that at the beginning, we might have overlooked them. But those remaining people will later build houses, open roads, light lamps, plant seeds, and create an entire city. Matter in the universe can be felt in a similar way, not winning through overwhelming numbers, but through a fragile excess after almost every symmetric pair had annihilated. What makes this story so profound is that this small excess did not simply remain without meaning. It became the material for every structure that followed. As the universe continued to cool, the extra quarks that were not annihilated with their corresponding antiquarks had the chance to enter more stable states. They would take part in the formation of protons and neutrons. Protons could later become the nuclei of hydrogen. Neutrons, when inside nuclei, would help form helium and heavier nuclei. The remaining electrons would later combine with nuclei to create neutral atoms. But all of these things needed one condition that was both simple and deep. Matter had to remain. If matter had been completely erased in its encounter with antimatter, there would have been nothing left to build with. We can say that the universe today is the story of a remainder. Not a remainder in the sense of something unnecessary, but a remainder in the most precious sense. Every atom in a stone, every water molecule in a drop of dew, every carbon atom in a cell belongs to the stream of matter that was not destroyed in the earliest moments. When we hear that, we do not need to turn it into something mystical. We only need to let that scientific truth settle in. We are not made from the main part of the original symmetry. We are made from the tiny part that broke the perfect balance. The universe perfectly balanced between matter and antimatter might be beautiful in terms of symmetry, but poor in terms of structure. It was the tiny imbalance that opened the door to a rich history. This also helps us understand why perfection does not always give birth to a world. In everyday life, we often think balance is the most beautiful thing. But in the early universe, perfect balance between matter and antimatter could have left almost no ordinary matter at all. What allowed stars to be born was not perfect symmetry, but a very small asymmetry. What allowed planets to form was not an absolutely equal division, but an excess of matter left after annihilations. What allowed chemistry to exist was not a piece of music with no deviation, but one tiny off note at exactly the right time. In its deepest beauty, the universe does not always need complete symmetry. Sometimes it needs just enough imbalance to create history. However, we also need to avoid misunderstanding antimatter as the enemy of the universe. Antimatter has no intention to destroy. It is not evil, it simply follows the laws of physics. When a particle meets its corresponding antiparticle, they can transform into energy. In modern laboratories, physicists can create and study extremely tiny amounts of antimatter using magnetic fields, electric fields, and vacuum conditions to keep it from touching ordinary matter. This helps test the fundamental properties of nature, such as whether antihydrogen behaves like ordinary hydrogen in certain precise measurements. These experiments are not dangerous games in the style of movie imagination. They are very delicate efforts to ask nature, how similar are matter and antimatter, and where are they different? That question points straight back to the first second. If there was an extremely tiny difference between matter and antimatter in the way they were created, decayed, or interacted under high-energy conditions, that difference could have been amplified into an enormous cosmological consequence. Matter remained. But to create matter asymmetry, the early universe needed more than just a difference between matter and antimatter. It also needed special physical conditions in which processes were not completely in thermal equilibrium. In other words, if every reaction had always been perfectly balanced by the reverse reaction, then it would have been difficult for any asymmetry to be preserved. But the universe was expanding and cooling, and that rapid change could have pushed some processes out of equilibrium, leaving long-lasting traces behind. This is where we see that the expansion of space was not just a background, it took part in the fate of matter. As the universe expanded, the temperature fell. As the temperature fell, some heavy particles were no longer created easily. As the environment became thinner, some interactions became too slow compared with the changing pace of the universe. Things that could previously have been reversed again and again now began to become locked in as leftover results. This was not a mechanical lock, but a way of saying that reactions were no longer fast enough to maintain perfect equilibrium. So matter survived not simply because some particle got lucky and avoided its antiparticle. It was connected to the entire rhythm of the universe changing state: expansion, cooling, imbalance, interaction, and probability. If we imagine the early universe as an extremely crowded dance floor, where every dancer has a symmetric dance partner, then expansion is like the floor constantly growing wider, the lighting changing, the music shifting rhythm, and the pairs no longer meeting in exactly the same way as before. Most pairs still find each other and leave the floor, but a very small number remain, not because they stand outside the laws, but because the laws of the whole room are changing. and those remaining dancers become the seeds of everything. This image is only an imaginative bridge, but it helps us feel what the physics is saying. The survival of matter was the result of a universe that did not stand still. Here, the silence of the story becomes very powerful. There was no explosion announcing that matter had won. There was no shining boundary dividing the universe into before and after. There was only a tiny imbalance in equations and particle processes. There was only an extremely small excess left after almost complete annihilation. But after hundreds of millions of years, that excess would flow into slightly denser regions under the pull of gravity. It would form the first gas clouds. Those clouds would collapse into the first stars. Stars would burn hydrogen into helium, and then in later generations forge carbon, oxygen, silicon, iron, and heavier elements. Planets would form from matter enriched by stars, and eventually part of that matter would become eyes looking up at the sky. It all began with the fact that not all matter was erased. It is worth noting that during the first second, we still did not have stable atomic nuclei in the sense that would appear a few minutes after the Big Bang. We did not have neutral atoms, we did not have stars to synthesize heavy elements, but the survival of matter during this stage was the required condition for the later steps to happen. This is the line between the world had not yet been created and the rules of the world had already been written. The first second did not create the carbon in your body, but if matter had not survived in the first second, carbon would never have had the chance to be forged inside stars. The first second did not create water, but if no protons had remained to make hydrogen, water would later have had no foundation for existence. The first second did not create planets. But without excess matter for gravity to gather, planets would have remained a possibility that never became real. And so, when we say antimatter almost disappeared, we should not understand that antimatter disappeared absolutely from every place and every situation. In modern laboratories, antimatter can still be created. In some high-energy processes in nature, antiparticles still appear. But on the scale of the observable universe, ordinary matter clearly dominates. The almost disappeared in the story of the first second refers to the fact that the original antimatter annihilated with corresponding matter so thoroughly that it no longer exists as a large symmetric component of the universe today. The remainder that built stars and galaxies was the excess matter. That truth has a very quiet beauty. The universe we see is not the result of abundance from the very beginning, but the result of fragile survival. A tiny part passed through the sea of annihilation. A tiny part was not cancelled out in the almost perfect symmetry. A tiny part had enough time to continue, then the strong force gathered quarks into protons and neutrons, then a few minutes later it took part in light nuclei, then hundreds of thousands of years later it became atoms, then hundreds of millions of years later it fell into the first stars. From this angle, the history of the universe is like a small flame protected in a fierce wind, so that much later it could become the light of countless suns. We can also feel the connection between this section and what happened before it. Space expanded, causing the temperature to fall. The falling temperature made forces and particles appear differently. Particles and antiparticles were created and then annihilated in the hot environment. The smaller symmetry between matter and antimatter left behind the excess matter. That excess does not stand alone as an isolated event. It is one link in the chain of transformations during the first second. If one link changed too strongly, the later story could be completely different. With too little excess matter, the universe might be poor in structure. With too many other conditions changed, later particle ratios could also be different. The first second is like a piece of music with very brief opening notes, but each note shapes the long melody that follows. This also helps us understand why the question "why is there something instead of nothing?" has a very specific version in cosmological physics. Why is there matter instead of only radiation? This is not a philosophical question floating in fog. It is asked through particles, antiparticles, conservation laws, symmetry violation, out of equilibrium states, and the expansion of the universe. The complete answer is still not fully in our hands, but that incompleteness makes the story more honest. We do not need to pretend that we know everything to see the wonder. Without a very tiny excess of matter, the entire material world would have had no stage on which to appear. And now, when we look back at ourselves, the story becomes very close. A hand resting still, a breath slowing down, a heartbeat moving steadily, all of it is made of matter. The protons in the atomic nuclei of the body did not come from some simple obviousness. They belong to the stream of matter that passed through a stage when matter and antimatter almost erased each other from the universe. A very small part remained. Then that very small part travelled through an unimaginably long history, from elementary particles to protons and neutrons to nuclei to atoms to stars to planets to biology. So when we say that the first second wrote the rules of the game, this is one of the most important lines in that rulebook. Matter had to remain, even just a little, for everything else to begin. There is a strange gentleness in that thought. We do not need to see ourselves as the centre of the universe in order to feel connected to the universe. We only need to understand that the matter inside us is part of that ancient remainder, a part that was not erased, a part that passed through the cooling of space, through the separation of the roles of the forces, through the almost complete annihilations, and then continued into the next chapter of matter. And that next chapter brings us to a very specific question. What did that surviving matter become in the following moments? The answer lies in quarks and gluons, in the strong nuclear force, and in the moment when the universe cooled enough that quarks were no longer free in the same way as before, but began to be confined inside more stable structures. From the fragile excess left after the annihilation between matter and antimatter, the universe would move toward a new milestone, the formation of protons and neutrons. There were no atoms yet. There were no complete light nuclei yet. There were no stars. But the deepest building blocks of nuclei were preparing to appear. And if the first second was the first rulebook of the universe, then this was when some of the first letters of matter began to be preserved long enough to continue writing the story. From the tiny amount of matter that survived the almost complete annihilations between matter and antimatter, the universe moved into another change that was also silent, but incredibly decisive. That remaining matter was not yet atoms. It was not yet atomic nuclei in the familiar sense either. It was still inside an environment so hot that stable structures had a very hard time staying in place. But as space continued to expand and the temperature continued to fall, the universe began to do something very profound. It turned ingredients that were still free, still violent, and still hard to grasp into particles that could later become the core of matter. This is where the story moves from quarks and gluons to protons and neutrons, from an extremely hot sea of particles to the first building blocks of atomic nuclei. To feel this transition, we need to enter a layer even smaller than the atom. In today's world, when we talk about matter, we often think of atoms. An atom has a nucleus in the centre and electrons outside it. Inside the nucleus are protons and neutrons, but protons and neutrons are not the final end of the story either. Inside them are quarks, held together by the strong nuclear force through force-carrying particles called gluons. If the electron is one of the familiar ingredients of the atom later on, then the quark is a deeper ingredient located inside the core of matter that we later call the nucleus. But in the extremely early universe, quarks and gluons did not behave as though they were sitting quietly inside protons and neutrons the way they do today. The temperature then was so high that matter could exist in a special state called Quark-Gluon plasma. This name can easily make us think of plasma in neon lights, lightning, or the hot outer layers of the sun. But Quark-Gluon plasma is not just ordinary ionized gas. It is a deeper state of matter, where quarks and gluons were not yet tightly confined inside particles like protons and neutrons. They were not completely free in a simple sense, like tiny marbles flying separately through empty space, but they were also no longer locked inside stable hadron structures the way they are in the cooler world that came later. During those extremely brief first moments, the universe was like a primordial liquid of subatomic ingredients, but the word liquid also needs to be used carefully here. We should not imagine it like water in a glass. It was a hot, dense state of matter, where quarks and gluons interacted strongly, transferred energy, and moved through an environment so dense that ordinary matter could not yet take on a stable form. If atoms are the complete sentences of the material world, then quark-gluon plasma was like letters, and syllables still moving through an enormous heat, not yet able to join into sentences. The strange thing is that the strong nuclear force, the force that would hold quarks inside protons and neutrons has a property very different from ordinary intuition. With the electromagnetic force, two charged objects can affect each other in a way that becomes weaker as they get farther apart. But with quarks, the story is not like that. Quarks are bound by the strong interaction, and in the cooler conditions of the universe, we do not see isolated quarks wandering alone. They are confined inside particles such as protons, neutrons, or other forms of hadrons. At extremely high temperatures, Quark-Gluon plasma allows a different kind of existence, where that confinement does not appear the way it does in the world today. As the universe cooled, that state could no longer continue as before, and quarks began to be gathered into more stable structures. This was one of the most important transitions of early matter. Before that, we can say the universe contained an extremely hot mixture of quarks, gluons, and many other particles. Afterward, as the temperature dropped past an important threshold, quarks began to combine into hadrons. Hadrons are particles made of quarks and affected by the strong interaction. Among them, the two most important characters in our story are protons and neutrons. A proton is made of 3 quarks. A neutron is also made of 3 quarks, but its arrangement of quark types is different from that of a proton. Thanks to that combination, matter began to have more stable particles that could continue through the later stages of the universe. Imagine a pottery workshop where the clay at first is too soft, too hot, and too restless to hold any shape. As the temperature and conditions change, the first blocks begin to harden, strong enough to be used later to build walls. The universe had no potter, no outside hand, no handcrafted design. But that image helps us feel what was happening. From a state too hot for familiar matter to stand firm, the universe began to have more stable particle blocks. There was no house yet, no walls, no roof. But the first bricks of atomic nuclei had begun to appear. The proton is especially important because it is the foundation of hydrogen. The simplest hydrogen nucleus is just 1 proton. Hydrogen would later become the most common element in the universe, the main fuel of stars through most of their lives. When a star like the Sun shines, it is turning hydrogen into helium in its core through nuclear reactions. But to have hydrogen, there first had to be protons, and to have protons, quarks first had to be confined in a stable structure. So when protons appeared in the early universe, that was not just a small detail of particle physics. It was a deep condition that allowed starlight to exist in the future. The neutron is also important, but in a different way. A free neutron is not stable forever like a proton under ordinary conditions. If it is not inside a nucleus, a neutron can decay after some time. But when a neutron is inside an atomic nucleus, it becomes an essential ingredient for forming nuclei heavier than hydrogen. Helium needs neutrons. Many heavier elements also need neutrons in order to have stable nuclei, so the number of neutrons left in the early universe was not a side issue. The ratio between protons and neutrons would directly affect the amount of helium created in the first few minutes after the Big Bang, when the universe became cool enough for light nuclei to form. This point needs to be made very clearly to avoid confusion. During the first second, the universe had not yet created complete atoms. Electrons had not yet been held around nuclei to form neutral atoms. Light nuclei, in the sense of Big Bang nucleosynthesis, also formed mainly later, when the universe was a little older during the first few minutes. But the first second had prepared the core ingredients. It created and gradually stabilized particles such as protons and neutrons, while also laying the foundation for the ratio between them. Without this step, the following minutes would not have had enough characters to create hydrogen, helium, and a small amount of primordial lithium. We can feel the subtlety of the universe here. Not everything important has to appear in a bright and spectacular form. Protons and neutrons do not shine like stars. They do not create a beautiful scene to be seen from far away. But they are more important than any scene, because they are the core of ordinary matter. If protons were not stable, hydrogen could not last for long. If hydrogen did not exist, stars as we know them would not have the original fuel they need to burn. If stars did not burn, later generations of heavier elements would not be forged inside stars and in the violent deaths of massive stars. If heavier elements did not appear, rocky planets, oceans, minerals, and biology would not have the familiar path that allowed them to be born. So in one very early moment, when quarks combined into protons and neutrons, The universe was not merely making a few tiny particles, it was giving matter its backbone. Up to this point, we have passed through an expanding universe, a cooling universe, a universe where the forces began to take on their own roles, and a universe where matter remained only because of a tiny excess after annihilations. Now, that excess began to take on a more stable form. It was no longer only a story of survival, it became a story of the ability to build. It is worth noting that modern physicists do not study this only through imagination. They study quark-gluon plasma in heavy ion collision experiments at large particle accelerators. When heavy nuclei are accelerated to extremely high speeds and then collide with each other, the energy concentrated in a tiny region can create small, short-lived droplets of hot matter, where quarks and gluons are released from the familiar structure of protons and neutrons. Those droplets exist for an extremely brief time and at an extremely tiny size. They are not the entire Big Bang recreated. They do not create a new universe. They only allow scientists to study a state of matter that is partly similar to conditions that once existed in the very early universe. This is a point we need to state with care. When people hear that accelerators create conditions like those after the Big Bang, it is easy to misunderstand that humans are recreating the Big Bang in a laboratory. A more accurate way to say it is this: experiments create extremely tiny, extremely hot regions of matter that exist for an extremely short time, so scientists can study the properties of matter under high energy conditions. They do not recreate the entire early universe. They do not have cosmic expansion like the Big Bang. They do not contain the full history of space-time, but they give us a small window into how quarks and gluons behave when matter is pushed into an extreme state. And through that small window, science has learned something astonishing. Quark-Gluon plasma is not just a messy cloud of particles flying around at random. It can behave like an almost perfect liquid, with very low viscosity. This makes the image of a primordial soup both approachable and something that must be understood correctly. Soup does not mean meaningless chaos. It is an image for a hot, dense, strongly interacting environment where the ingredients are no longer confined inside ordinary particle structures. Its liquid nature does not make the story simpler. It makes the story deeper. Even in one of the most extreme states, matter still has collective properties, still has laws, still has ways of flowing, reacting, and transferring energy. Let us return to the young universe. As quark-gluon plasma cooled, quarks did not continue in that state the way they had before. They were confined into hadrons. This process is often called the quark-to-hadron transition. In a gentler telling, we can say that matter was solidifying at the subatomic level, not solidifying into rock, not solidifying into ice, but solidifying into more stable particle structures. Protons and neutrons began to become entities that could last through cosmic time, long enough to take part in later stages. The universe was still terribly hot. The universe was still not transparent. The universe still had no atoms, but it had crossed a threshold. The particles that would become the cause of atoms had appeared. We should pause for a moment before this truth. When people say atom, many may imagine a small model with a nucleus in the centre and electrons moving around it. But before that model could exist, there first had to be nuclei. Before there could be nuclei, there had to be protons and neutrons. Before there could be protons and neutrons, quarks had to be held inside stable structures. And before quarks could be held, the universe had to cool enough after its first moments. So just a small drop in temperature in the early universe changed the entire future. At higher temperatures, matter existed in a different form. At lower temperatures, protons and neutrons could form. A small change in the early conditions became a turning point for billions of years that followed. If we want to understand what it means to say, the first second wrote the rules of the game, this is a very clear example. That rulebook was not an abstract sentence. It was the strong nuclear force beginning to confine quarks. It was the proton becoming a stable particle. It was the neutron appearing in enough quantity to later take part in helium. It was matter no longer being only a hot stream of energy and scattered particles, but beginning to have more stable units so history could continue to build. The universe did not need to create stars during the first second. It only needed to create the right kinds of particles so that one day stars could form. There is a calm but very deep way to see this. The proton is one of the anchors of matter. In a universe that is always expanding, always changing, The proton brings a strange kind of stability. It can exist for a very long time. It can become the nucleus of hydrogen. It can take part in stars, water, organic molecules, and living matter. When a star burns hydrogen in its core, when a drop of water exists on a planet, when a molecule in the body is held together by chemical bonds, underneath all of that is the presence of the proton. And that proton could only enter the story because, at an extremely early moment, quarks had been confined inside a stable structure. The neutron is like a less stable companion when it stands alone, but it is incredibly necessary when it is part of the community of a nucleus. If there were only protons, the universe would have hydrogen, but it would not easily build the richness of other nuclei. Neutrons help nuclei move beyond the limit of simple hydrogen. In the first few minutes after the Big Bang, neutrons together with protons would form deuterium, then helium, and a small amount of lithium. Later, inside stars, neutrons would also play a role in many processes that create heavy elements. But everything begins with the question in the first second: how many neutrons remained? How quickly did they decay? How long did the weak interaction keep them in balance with protons? As the universe expanded, when did those ratios begin to stop changing easily? This question brings us close to the next part of the journey, the proton-to-neutron ratio. But before moving there, let us hold on to the meaning of the present moment. The universe did not merely let matter survive. It began to create more stable forms of matter. If the previous section was the story of a small amount of matter not being erased, then this section is the story of that matter beginning to find structure. A person who survives a storm still needs shelter, tools, and seeds. Matter that survived annihilation was similar. It needed protons and neutrons to become the foundation of nuclei. And by cooling down, the universe opened that door. This did not happen in one separate place in the universe. There was no single central region where protons and neutrons were born and then flew outward. In cosmological models, the transition happened throughout all observable space at that time, because the entire young universe was in a hot, dense state and was cooling down. Every place in space was part of the shared process. This is why we should not imagine a small factory at the center of the universe producing particles. The universe itself was the environment. Expansion itself was the clock. Temperature itself was the door deciding which state was allowed to exist. And when we look back from the present, each proton in our body is like a very deep memory of that moment. Not memory in the conscious sense, but physical memory. It carries within it the result of the strong force of quark confinement, of a universe that had cooled enough for hadrons to appear. Those protons may later have passed through many stars, many gas clouds, many generations of celestial bodies. But the deep origin of that particle form lies in a time when the universe was younger than all scenery, younger than all starlight, younger than every neutral atom. When we say matter has a history, that history does not begin with planets. It begins with particle transitions in the first second. Perhaps the most beautiful part of this section is the contrast between smallness and enormous consequences. Quarks are so small that the naked eye cannot imagine them. Protons are much smaller than atoms. Neutrons are too. The processes that formed them happened in a time so short that human life has no matching intuition for it. But without those tiny processes, no large structure would appear later. No Milky Way, no Sun, no Earth, no layer of rock beneath our feet, no ocean, no body breathing. The vast universe was built on subatomic changes that happened in the silence of the first second. So when we hear the phrase Quark-Gluon soup, we should not treat it as a strange-sounding image and then move past it. It is one of the earliest states of matter after the Big Bang that science can study through theory and experiment. From that state, as the universe expanded and cooled, quarks were no longer in plasma form as before. The strong force gathered them into hadrons. Among those hadrons, protons and neutrons became the main characters in the history of ordinary matter. This was the transition from matter too hot to build into matter that began to have the ability to build. It did not create the house, but it created the bricks. It did not light the stars, but it prepared the nuclear fuel for stars. It did not create atoms, but it created the cores that atoms would need. And at this point, the universe still looked nothing like the familiar world. There was no night sky, no slowly rotating galaxies, no cold, rocky planets, no neutral atoms. But something very basic had arrived. Protons and neutrons had entered the story. These particles would continue into the first minutes, where they could combine into light nuclei. Before that happened, the universe still had to pass through another important step. Neutrinos gradually separated from the hot flow of matter, and the ratio between protons and neutrons began to be fixed in a way that affected the amount of primordial helium. In other words, the first skeleton of matter had formed, but the universe still needed to determine the proportions of those bones before the first nuclei could be born. So if we had to keep only one message from this stage, remember this: the first second did not create a complete world. It created the possibility that a world could be built. From the tiny amount of matter that had survived, quarks and gluons passed through a profound transition. Quarks were confined into protons and neutrons. Protons opened the way for hydrogen. Neutrons opened the way for helium and more complex nuclei. And from those silent particles, much later, the universe could have starlight, elements forged inside stars, planets, water, rock, and a mind quiet enough to look back and ask, in that first second, how did matter begin to have a backbone? Once protons and neutrons had entered the story, the universe was still far from quiet. It was still a hot, dense environment, filled with radiation and particles moving without pause. But compared with the very first moments, the universe near 1 second old had changed greatly. It had expanded. It had cooled. It had moved away from the extremely intense original state, where forces, particles, and interactions were blended together in a sea of energy that was difficult to distinguish. Now, within heat that was still far beyond anything familiar in everyday life, the universe began to pass through another subtle transition. Some particles were no longer held tightly in the shared flow of collisions. Among them, the neutrino was an almost invisible character, but it played a very important role. Neutrinos are very light particles that interact very weakly with matter. If electrons, photons, protons, or neutrons leave more noticeable traces in physical processes, then neutrinos are like guests passing through a room while barely touching anything. In the universe today, countless neutrinos can pass through Earth, through our bodies, through rock, water, and air, almost without being stopped. They interact so rarely that to detect them, humans have to build enormous instruments, placed deep underground, beneath ice, or inside extremely quiet environments, just to wait for a very small number of rare collisions. But in the early universe, everything was very different. When the universe was still extremely hot and extremely dense, even particles that interact as weakly as neutrinos could collide, often enough with other particles to remain part of the shared plasma. Plasma here was not an ordinary flame, but a hot environment made of radiation, charged particles, light particles, heavier particles, and constant interactions. In that environment, neutrinos had not yet fully followed their own path. They were still exchanging energy with the rest of the young universe through the weak nuclear force. But as space expanded, the density dropped. As the density dropped, the average distance between particles increased. As the temperature fell, the energy in collisions also decreased. And when the universe became thin enough, the already rare, weak interactions of neutrinos no longer happened quickly enough to keep them blended into the shared plasma. We can imagine this as a room that was at first so crowded that even if everyone spoke very little, they still kept brushing shoulders. But as the room grew wider very quickly, each person slowly moved farther away from the others. The shoulder brushes no longer happened often enough. From that moment on, each person began to move in their own direction. Neutrinos in the early universe were similar. When the universe was about 1 second old, they began to separate from most of the hot matter and almost drift freely through space. This separation did not create a dazzling scene. No new light burst forth for human eyes to see. There was no clear boundary like sunrise on the horizon. But physically, this was a very important milestone. It meant that the universe was no longer a completely shared system of interactions as before. One component began to leave the continuous flow of collisions and carry its own history. Neutrinos became a very early kind of memory of the universe. If we could directly measure the primordial cosmic neutrino background, we would see a signal far older than the cosmic microwave background that telescopes have mapped. But because neutrinos interact so weakly, directly detecting that neutrino background is still an extremely difficult challenge today. This helps us understand another important point. The oldest light we can observe through the cosmic microwave background is not the light of the first second. The cosmic microwave background was released much later, when the universe was about a few 100,000 years old, at the time when electrons combined with nuclei to form neutral atoms and the universe became more transparent to light. During the first second, photons were still trapped in a dense environment, constantly scattering off charged particles. So if we want to look for a trace closer to the first second, neutrinos are a deeper candidate than light. They left the plasma much earlier, but precisely because they are so quiet, they are extremely hard to catch. Alongside neutrinos, another change was also taking place near the end of the first second. The ratio between protons and neutrons was beginning to take shape. This detail may sound small, but it was actually like the universe weighing out the ingredients for the first light nuclei. Protons and neutrons could transform into each other through weak interactions in the hot environment. When the universe was still very hot, those processes happened often enough to keep protons and neutrons in a kind of relative balance. But as the universe cooled, the weak reactions slowed compared with the expansion rate of the universe. At a certain point, they could no longer keep the proton and neutron ratio changing as flexibly as before. That ratio began to close in gradually, like a number being written into the universe's first draft. Why was this ratio so important? Because a few minutes later, when the universe was cool enough for light nuclei to form and remain more stable, protons and neutrons would combine to create deuterium, helium, and a very small amount of lithium. If there were too many neutrons, the amount of primordial helium would be different. If there were too few neutrons, the amount of helium would also be different. If the universe had expanded faster or slower in a different way, the amount of time neutrons had to decay before being locked into nuclei would also have changed. So a particle ratio prepared near the end of the first second could influence the light element composition of the entire universe. This is where we need to be very clear, because it is easy to misunderstand. During the first second, the universe had not yet created complete atoms. Electrons were not yet resting around nuclei to form neutral atoms. Light nuclei had also not fully formed during the first second in the sense of Big Bang nucleosynthesis. The process that created most of the primordial hydrogen, helium, and a little lithium happened during the first few minutes when the universe had cooled even more. But the first second prepared the decisive conditions for that process: temperature, density, expansion rate, the number of protons, the number of neutrons, and the separated state of neutrinos. In other words, the first second had not yet written the complete piece of music, but it had set the rhythm, chosen the instruments, and determined the opening notes. Imagine a concert before the first sound is played. The hall is still quiet. The audience has not yet heard the melody, but the conductor has raised a hand. The musicians have placed their hands on the strings, the keys, and the drum heads. The sheet music is open on the stands. The first beat is about to fall. If one instrument is missing, if the opening rhythm is off, if the whole orchestra is not ready, the melody afterward will be different. The universe near the end of the first second was similar. There were no light elements in the complete sense yet. There were no atoms. There was no free light. But the conditions for the first nuclei to be born in the next few minutes had been put into place. This is exactly what makes helium in the universe such profound evidence. Helium is not created only inside stars. It is true that inside stars, hydrogen can fuse into helium and release energy, helping stars shine. But a large amount of helium in the universe originated from a very early period during the first few minutes after the Big Bang. That means when we measure the composition of light elements in the universe, especially hydrogen, helium, and deuterium, we are not just doing ordinary astrochemistry. We are reading traces from a time when the universe was so young that there was not a single star yet. The primordial helium composition is like a faint but durable line of writing, written by temperature, density, and the proton-to-neutron ratio from the earliest moments. And here, neutrinos return to the story. Neutrinos did not simply leave the plasma and then lose all physical meaning. They contributed to the radiation energy density of the early universe. That energy density affected the expansion rate. The expansion rate then affected the moment when weak interactions could no longer maintain the proton and neutron balance, and it also affected the process of light nucleus formation afterward. So particles that are almost invisible, particles that barely touch matter today, indirectly influence the amount of helium the universe created in its earliest period. This is one of the beauties of cosmic physics. Sometimes the quietest character helps determine the structure of the entire story. We can see the whole first second as a chain of doors opening and closing. When the universe was too hot, the doors to stable matter had not yet opened. As it cooled, the natural forces separated into their own roles. As matter and antimatter annihilated each other, only the excess matter remained to continue. As quarks and gluons transitioned into hadrons, protons and neutrons appeared. As neutrinos separated from the plasma, one component of the universe began to drift freely. As the proton and neutron ratio took shape, the universe prepared for light nuclei. Each door opened during an extremely brief period of time, but its consequences lasted for billions of years. If we looked with ordinary eyes, we could not see any of this. No colours, no shapes, no surfaces, nowhere to stand and observe. But if we look with scientific thought, we see an order forming. The universe was no longer a completely undifferentiated state. It had types of particles with their own roles. It had interactions separating from one another. It had surviving matter. It had protons and neutrons. It had neutrinos beginning to follow their own path. It had the conditions for light nuclei to appear a few minutes later. The universe still did not have the familiar world, but it already had the basic alphabet from which the familiar world could be written. We should also remember that the first second cannot be photographed with ordinary telescopes. Telescopes see light. But the freest light we can observe from the deepest past comes from a much later period, when the universe became transparent. Before that, the universe was a thick plasma fog for photons. So when science talks about the first second, it is not relying on a direct picture. It relies on many connected layers of evidence: the expansion of the universe, the cosmic microwave background, the composition of light elements, particle physics, thermodynamic models of the early universe, and experiments that help test the behavior of matter at high energy. This work is like reconstructing an ancient piece of music from vibrations left on stone walls. No one can still hear the original sound directly, but there are enough traces for us to know what rules the music once followed. So near the end of the first second, the important point was not that the universe had become familiar. It had not become familiar at all. It was still so hot that nothing in everyday life can compare with it. It was still too dense for light to travel freely over long distances. It still had no neutral atoms, no stars, no galaxies, no planets. But it had already passed through a series of foundational transformations. From an initial hot and dense state, it had expanded and cooled. From a picture of forces and particles that was hard to distinguish, it now had clearer natural roles. From almost complete annihilation, it had kept a small amount of matter. From quarks and gluons, it now had protons and neutrons. And from the shared plasma flow, neutrinos began to separate, while the proton-to-neutron ratio was being prepared for the stage of light nucleus formation. If we place all of that into one slow sentence, then when the first second ended, the universe was like a structure with no outer form yet, but with its deepest foundation already driven into place. No walls, no windows, no lights, but the ground had been measured, the first pillars had been set, the most important materials had been chosen, and from here, time could continue building. A few minutes later, light nuclei would form. Hundreds of thousands of years later, neutral atoms would appear, and light could move more freely. Hundreds of millions of years later, the first stars would burn. Billions of years later, galaxies would turn slowly in the dark, planets would cool, and part of that ancient matter would become life capable of listening to its own story. What makes the first second so wondrous is not that it created everything. If we said that, we would distort the real beauty of science. The first second did not create oceans. It did not create the carbon in the body. It did not create the night sky. It did not create the Milky Way as we see it. But it set the conditions without which all of those things would have had no path to appear. It was like the first lines of nature's code, not the complete program, but enough to determine the first rules. When neutrinos separated, when protons and neutrons entered their own history, when the ratio between them began to matter, the universe was quietly preparing for the next chapter, the birth of the light nuclei. And this is where the story of the first second closes very quietly. There was no bell announcing that the universe had reached 1 second old. There was no line drawn across space saying that one stage was finished. But if we could look with imagination guided by science, we would see a profound change. The universe was no longer a completely undifferentiated hot sea. It had particles that would become atomic cores. It had almost invisible particles drifting freely. It had matter ratios that would determine the amount of primordial helium. It had light still trapped in plasma, waiting for a much later era to become free. And most importantly, it had a path. That path would go from protons and neutrons to light nuclei, from light nuclei to atoms, from atoms to cosmic gas, from cosmic gas to stars, from stars to heavier elements, from those elements to planets, and finally to structures that could ask about their own origin. All of that was still very far away. But the direction had opened. So when we think about the first second after the Big Bang, we should not think only about violence. We should also think about preparation. In a moment shorter than a breath, the universe did not create the world as we see it today, but it had written enough of the first lines for that world to no longer be impossible. And so, when we look back at the first second after the Big Bang, we are not only looking at one brief moment in time, we are looking at the place where the most fundamental conditions of the universe began to fall into position. In that first second, not a single star was shining yet. No galaxy was slowly turning in the darkness. There were no planets, no oceans, no rocks, no complete atoms, and no empty space in the way we usually imagine it. But right there, in heat and density far beyond all intuition, the universe began learning how to become a place where matter could exist. Space expanded. The temperature dropped. The natural forces gradually took on their own roles. Elementary particles appeared in the hot sea of energy. Matter and antimatter almost destroyed each other, but a tiny amount of matter survived. Quarks combined into protons and neutrons. Neutrinos separated from the hot plasma, and the ratio between protons and neutrons began preparing the way for the birth of light nuclei in the next few minutes. None of this had created the world as we see it today, but it had written the first lines of the rulebook that made today's world possible. Seen this way, every atom in our bodies does not belong only to Earth. It belongs to a much deeper history, one that began when the universe was younger than a single breath. Before there was gentle starlight, before there was a night sky, before there was life capable of asking questions, the universe had to pass through that first second to preserve matter, to form the first particles, and to open the long path that would lead to everything. Thank you for travelling with Drift into Quiet, knowing back to the first moment of the universe. Let this thought settle slowly. Sometimes the greatest things do not begin with a dazzling scene, but with quiet laws written in silence. Sleep deeply, sleep peacefully. And I will see you again on the next journey, as we continue listening to the deeper stories of the universe.